data visualizations are not primarily visual. Data visualizations are primarily structural. I think this is something you all have an intuitive sense of. You just may not have thought about it that way or heard about it that way. If they were primarily visual, this wouldn't be a technical conference. This would be a conference about aesthetics or counting blocks and dots and lines. But no, they're structural. They explore relationships, patterns, trends, outliers. Ultimately, data visualizations, like any kind of communication, is about creating a working model, taking the working model from your own head and packaging it up so that someone else can unpack it into their own head and have their own mental model of it. But everyone learns and understands different things in different ways at different paces. So if something is especially important, you should make it explicit and obvious. And also, to be inclusive, you should provide different sensory modes to access that information, not just the visual. I'm not saying that the visual aspect of data visualizations is not important. It is, absolutely. But there's more to it than that. And that more to it than that is accessibility. I've been thinking about accessibility in data visualization for a long time. And here's sort of the stages of data visualization accessibility awareness that most people seem to go through. First, we start thinking about colorblind safe palettes. We want to use good colors to make sure that we're not excluding people. And then we realize, wait, it's not just about colors. We need to think about blind people and how a screen reader can access this information. But when you're accessing one bar at a time or one data point at a time, that's a lot of information. So we realize, oh, wait, there's actually a lot of information for everybody to process. And we start thinking about cognitive accessibility. Oh, how are we going to deal with this cognitive accessibility, making sure that the user experience is available to everyone? And then we start thinking and realizing that all UX is accessibility. And that's when we've gone too far, because all UX is not accessibility and all accessibility is not UX. It is, if you conflate those two things, you run the risk of ignoring very specific and technical necessities that apply to specific kinds of disability. So I wouldn't conflate those two. But in general, we're going to talk today about designing data for cognitive load. My name is Doug Schepers. I work for Phys Studio. We do software and consulting on making data visualizations accessible. You can email me at doug@phys.studio or hit me on the socials at Shepazoo. So, in the 1980s, Edward Tufte, who I'm sure most of you are familiar with, was advocating for simplicity in charts, and he introduced terms like chart junk, and the data to ink ratio. Meanwhile, halfway across the globe in Australia, an education researcher named John Sweller, at the same time in the 1980s, developed something called cognitive load theory, and he introduced this as a pedagogical or a teaching methodology. So why am I talking about a teaching methodology at a data visualization conference? Am I at the right conference? I think that actually data visualization and teaching have a lot in common. They're both go back to that mental model. They're both about taking a complex subject and packaging it up so that it can be unpacked in somebody else's brain. In addition, there are many analogs between data visualization best practices and cognitive load theory, or CLT. Tufte talked about chart junk. What is chart junk? Chart junk is the kind of extra bits that we put on data visualizations to make them meet a certain aesthetic. Like for example, these 3D bars that were popular in the 1980s, and I've seen them still used. That's chart junk. And in CLT terms, that's removing that is about reducing the extraneous load. I'll get to extraneous load in a bit. Then there's the data to ink ratio. In addition to removing unnecessary, or in addition to reducing flare, we can also every bit of Tufte said every bit of ink, or pixels in our case, that's being used in data visualization should go directly towards conveying the data. Now, that's not always true, but it is a good rule of thumb. And in CLT terms, that's optimizing intrinsic load. Then we get, so let's remove that. Let's remove those lines and let's just make a nice, clean data visualization. And then we've got this false color coding. Do each of these bars really encode a different piece of information, or is it just there to add some visual appeal? Well, if it's just there for visual appeal, it can be confusing. So we should remove that extra encoding. In CLT terms, this is approximately something called redundancy. So here we have a nice, clean, clear data visualization. And we've applied some data visualization best practices. And those are also best practices. Those are actually real-world examples, or rather real-world data about how humans process information. CLT provides that to us. It is a methodology that has been studied scientifically. Those studies have been peer-reviewed. They've been reproduced and duplicated. They've been applied in the education field for decades. So we've really got a solid foundation, not just our intuition, but actually what is shown to work. And I think that's a really interesting thing to explore. So let's explore it. I'm going to talk a lot about disabilities in this presentation because cognitive load affects everyone, but the effects are magnified in many people with disabilities. So this is in general for everyone, but there are some specific considerations for accessibility. For example, blindness. Blind people using a screen reader typically have sequential data point access. That means they access each data point at a time. And trying to keep all of these in mind taxes the memory. And as you can see, it's clearly harder to recognize patterns when you're just seeing a piece of the picture at a time. And speaking of a piece of the picture at a time, there are low vision users. They use a zoom and pan technique. So you zoom out to see the big picture, and then they zoom in to see the details. So they might have a limited overview and recall triggers, visual recall triggers, and it's going to be harder for them to notice changes in some part of the viewport that they aren't looking at. But I also want to emphasize that data visualization is really useful for people with low vision. Much more useful than a data table because big blocks of color are much easier to perceive than tiny little numbers that all look very similar when your eyesight isn't perfect. And then there's cognitive disabilities. This is everything from ADHD, which I have, to dyslexia, to all sorts of more serious conditions, anything in the autism spectrum, anything having to do with traumatic injuries to memory or to mental processing, attention management. So as you might expect, this is a strong impact by cognitive load. These people may be distracted easily from details and goals. They may be more literal minded. Basically, they can be overwhelmed by lots of things, including data visualizations. So let's get that animation off the screen so it's not distracting us anymore. I want to talk about intrinsic versus extraneous cognitive load. Cognitive load isn't just the amount of mental effort something takes. You can break it down into different aspects. Intrinsic cognitive load is that bit that is the core idea. That's the central idea. It always takes some minimal amount of mental effort to understand something. Then there's the extraneous cognitive load. This is everything that's not the core. It's the clutter, it's the redundancy, it's everything else. And then there's something called germane cognitive load. Germane cognitive load, it's the brain looking for patterns within the clutter to develop context to be able to better understand the intrinsic load. Obviously, sequential tasks, such as screen reader users, low vision users, voice users in general, those are going to cause more cognitive load than parallel tasks where you're seeing everything at once. And processing text as opposed to graphics introduces additional cognitive load and exertion. So we want to minimize that. And I'm fond of saying that we should simplify data visualizations. When you're making a chart, write a poem, not a novel. But simplifying is not always enough. We've got our working memory capacity. That's our bottleneck. When we have extraneous load and intrinsic load combined together, when that exceeds our working memory capacity, that leads to the reader being confused and overwhelmed. But if we don't optimize that, if we don't have enough intrinsic load and extraneous load, that leads to people being bored or disengaged. I hope you're not bored or disengaged at this point in my presentation. So we really want to balance these things. We want to reduce the extraneous load, and we want to optimize the intrinsic load. Now, cognitive load theory has a lot of different effects and principles that go along with it. We can't cover all of them today, but many of them are directly applicable to data visualization. And a key thing to remember is that different users need differing amounts of support depending upon their level of expertise. And so we should try to balance between less experienced and more experienced users of data visualizations every time we make a chart. One of the underlying principles of memory and thus cognitive load theory is the idea of chunking and automating. So we've got our brain, and then we've got our environment. Our environment is unlimited. There's an infinite amount of stuff in the environment. And some of that stuff comes through our senses into our brain, whether through the eyes, the ears, the sense of touch, and then it passes into our short-term memory, and that's got temporary recall and low capacity. And from our short-term memory, it passes into our working memory. Our working memory is where that information is encoded and stored in our long-term memory. This is where our long-term memory has semantic content, meaningful content. And it also has effectively unlimited capacity and indefinite duration. The indexing is not always great, but we don't know of specific limits on memory, on long-term memory, rather. So that means that working memory really is the bottleneck. That's where our limited capacity for working memory stops us from being able to process things that are very complex or beyond us. So what does the brain do? It does something called chunking. It combines complex familiar ideas and tasks through analysis, through repetition, through practice. It combines these complex ideas into a single unit to automate that cognitive processing. So if we see something that's familiar to us and something that's unfamiliar to us, we can take the familiar part to help us contextualize the unfamiliar part. And that's where we get into something called preteaching. Of course, we're talking about teaching because cognitive load theory is primarily about education. But and in education, they talk about preteaching. They say, okay, introduce ideas slowly, build on each foundational idea until you get to more complex things. So the lesson we can apply to data visualizations is use familiar chart types wherever possible. That way, if somebody's familiar with the chart type, all they need to do is interpret it to get the data out. You're not putting a block between them and the data. They can more quickly get at that data. That's not always possible. Sometimes we want to have novel chart types. When we do have those novel chart types or interactive chart types, we should provide instructions on how to use those chart types so we don't lose somebody's ability to process the information. Basically, we should introduce ideas gradually before exploring new ideas in depth. Another effect studied in cognitive load theory is the split attention effect. This is really directly related to charts. In fact, they did specific studies with charts. The idea is that closely related information should be placed together in time and space. Here we have an example of a legend versus direct labeling. With a legend, I'm looking at the color or the shape or both, and I'm trying to remember what that stands for. Then I move my eyes up to the line, and I have to memorize each of these legend items and apply them to the line. And that takes cognitive load. It increases the cognitive load. So if we have direct labeling, we can forego all that. Direct labeling removes the need for a legend. It helps people with low vision and color vision deficiency, and obviously it's good for cognitive disabilities like memory and abstraction problems. Obviously, though, we can't always get rid of legends. They're sometimes necessary. If we have multiple values we're trying to encode in one chart and we can't get away from that, then yeah, use legends, but also include things like pop-ups, highlights, or other interactions that can add additional encodings, and also explain how the user can use those things. When you do so, ensure all those interactions are also accessible via keyboard, touch, and voice, by the way. We get to another CLT effect called segmentation. We want to reduce intrinsic cognitive load by breaking up those tasks into bite-sized chunks, both conceptually and visually. Conceptually, that might mean something like taking a complex chart and breaking it down into multiple simple charts. And visually, that means, for example, separating different segments by white space or empty space between them, so that someone can visually see the distinct items rather than process them as individual things, as opposed to just one thing or one big thing that they have to sub-process. So we're doing a little bit of the work for our users. We're sort of chunking and automating for our users. And this has some good implications for the Web Content Accessibility Guidelines, the W3C official guidelines for accessibility. Part to whole versus whole to part is another critical effect that's been studied in cognitive load theory. Sequential readers, like screen reader users, low vision users, people with memory problems, or just anybody who's distracted, for example, they might see only one part of the puzzle at a time. You have to remember the previous piece while listening to each new piece to attempt to construct the whole in their mind. Obviously, this can get really confusing. Most readers see both the whole and the parts at once, but not everybody does. So initial summaries help readers put each piece into the context of the whole. So if you contextualize what somebody's going to see, they understand it better. and they can start putting those pieces together and come up with a better picture of the whole. Now, that's not always possible when you have dynamic charts. It's not always possible to write alt text or summaries. But what is possible is you can always add interpretation instructions for tasks, the things that people are likely to see and how they should interpret them when they see them. And that brings us directly to something that's not cognitive load theory, but which is part of accessibility, and that's alt text. Alt text is the sort of the summary that that you provide for an image in HTML. So you should always provide for your charts some alt text, or better yet, a caption or a summary that everybody can see. And a good way of thinking about this is you should compose the alt text like you're describing the chart to somebody over the phone. Amy Cecil wrote a great article called Writing Alt Text for Data Visualization. And she suggests the following sort of methodology. The alt text should be the chart type of data where reason for including chart. And then she also suggests including a link to the data source somewhere in the text, which is also a good practice. So, for example, the alt text here might read, bar chart of global competitive infrastructure index for different countries where the United States is tied for fourth place. Why do we say the United States? Because the United States is that yellow bar as opposed to the blue bar. So it's obviously we are saying the yellow bar is being conveyed as something special in this visualization. So we convey that in the alt text. So what are our takeaways here? Cognitive load theory was developed for rigorous instructional design. But we can remap learning to rapid absorption of new information through data visualization and benefit from a large body of scientific research on how people process information. We can take our best practices, we can validate those best practices, or invalidate what we think are best practices. We can take the lessons from cognitive load theory and have new ways to think about making our data visualizations more inclusive and accessible to people. When I was doing research for this idea, a really nice intro that I found was Cognitive Load Theory in Action by Oliver Lovell. It has a really good summary of the CLT principles, and it was written for teachers, obviously, but it is adaptable to designers, data designers. All we need to do is we need to reduce the extraneous pedagogy information and optimize the data viz applications. And I think that cognitive load theory is a really interesting lens to view data visualizations through. And I hope that it's useful to you as well. If it is useful, get in touch with me. Thanks for your attention. My name's Doug Schepers at Viz Studio. And if you have any questions, comments, or suggestions, please reach out. Thanks.